Good afternoon, students. Right, so of course we are having our quiz 1 today. Right, will be conducted from 2 p.m. onwards. Right, so the first part of the lesson, I will still go through the material and I will finish topic 2 today. Okay, so that tomorrow during the tutorial, I will probably continue with topic 3. Okay? Yeah, so I'm going to talk about the intermediate value theorem, right? Actually, this is a theorem that is kind of logical, okay? Because it just basically states that, okay, it's a continuation of the idea of continuity, okay? Which says that, well, if you have a function curve that you can draw in one stroke from some point A, x equals to A, to another point, x equals to B. So as long as you can draw in one stroke, one continuous stroke, okay? Then that means you must be guaranteed that you are able to find some intermediate value, let's say n, that is in between f of A and f of B. So actually that's it. That's the intermediate value theorem, okay? So basically, in the layman analogy, right, of let's say growing up, basically your height has to reach 120 cm first before reaching a higher height, let's say 160 cm. Okay, because the growth in height logically will be continuous. Okay, you don't suddenly like jump, right, in some value of your height, right, at some instant. Okay, so therefore, because growth in height is continuous, that means you must reach the intermediate value of 120 cm first before reaching a higher number, let's say 160 cm. Okay, so I think this layman analogy will explain clearly, right, what is this concept of the IVT here, intermediate value theorem. Okay, so you can also observe that the two graphs here, they are both continuous and they both satisfy the IVT. And notice that the first graph, it only satisfies the IVT at one point n. Okay, that means whereby C is, there's only one point C in between A and B, right? Such that f of C is in between f of A and f of B. Okay, so this can be just one point, but this can also be multiple points. Because from the graph here, you can see that it's continuous, right? This is clearly continuous. And as long as your interval is closed, A to B is closed, meaning to say it includes the endpoints A and B. Okay, then you can see that actually I can find multiple values between A and B, right, such that I get the intermediate value of f of C. Okay, so it can be C1, C2, C3, right? So of course, the wavier your function is, then certainly the more points you will find, okay, that you can satisfy some intermediate value. All right, so this is the concept of the intermediate value theorem. Basically, it's a statement of continuity, okay, which means that the conditions will be such that the function must be continuous, then you can apply this intermediate value theorem. Later on, we're going to see how we can apply this concept practically. So therefore I stated here that it is very important to firstly verify first the continuity of the function in the given interval. Because if this is not achieved, then you cannot apply IVT. That means you cannot say that you are guaranteed to find some intermediate value. Okay, so this one must check, right? And you can actually easily understand why is it that you cannot apply IVT if the function is not continuous. Like for example, this guy here. Okay, so let's say if you are looking at the function 1 over x, right? But because 1 over x has an infinite discontinuity at x equals to 0, so it violates the condition of the intermediate value theorem. And it doesn't apply. Why is that so? Because if I ask you, what is the value of C in between -2 and 2, right? Such that you can give me 0. That means the function must give me 0. Then you realize that actually there's no such C inside -2 to 2. Okay? Because f equals to 0 is simply not in the range of the function 1 over x. Okay? So you can see, I can easily disprove, right, that you can use IVT if your function is discontinuous. Can Because the discontinuity actually allows one, right, to jump from one point to another point, right, without so-called passing through the intermediate points. Okay, that's the main idea. So let's take a look at the exercise here. Which of the functions below can the IVT apply in the interval minus 5 to 9? Minus 5 to 9, okay? So in this concept, right, you can see that, the first function, g of x, equals to this cubic function. But we know that cubic functions are continuous everywhere, what? Correct or not? I mean, as in like polynomials are the continuous everywhere, ma. You can just draw a curvy polynomial function, right, in one stroke, okay, without lifting up your pen. So therefore, right, this can definitely apply, okay? So for G, right, the answer is yes. So yes, since G is continuous everywhere. Continuous everywhere. In R lah, okay? So that's for part A. Then for part B, H. So is H open to applying of the intermediate value theorem? For this H equals to ln x. And it must be between minus 5 to 9. So the answer here is no. Very good. Okay? So here is no. Since H is not defined. Because it is not defined for the negative values and 0 values of x, right? For x less than or equal to 0. So it cannot be continuous from minus 5 onward. Okay, because if you try to, give it any negative x, it is undefined. So how can it be continuous in the negative part of the domain? So what about C? C. Is C continuous, or can C apply IVT? Yes? Very good. The answer is yes. Yes, because the discontinuity is at x equals to minus 6. Yes, since discontinuity is at x equals to minus 6. So which means that the interval, okay, what? Minus 5 to 9 is perfectly fine. So P of x is continuous in minus 5 to 9. Okay? So it doesn't mean that, this point demonstrates that it doesn't mean that as long as you have a continuity, you cannot apply the intermediate value theorem. That's not true, right? It must be the continuity in the given interval. Okay? So as long as your function has no discontinuity in the given interval, then you can apply. Okay? Now about D. So D, I think you probably know that the answer is no. No, okay, because x equals to minus 1 is inside the interval. So no. Since discontinuity at x equals to minus 1 is in minus 5 to 9. Okay, so basically the 4 functions given here are just to demonstrate that you really need to check the continuity of the function in the given interval before you can decide whether you can apply the intermediate value theorem or not. Any questions? Good. So actually this intermediate value theorem is one of the first steps that you need to apply before you try to solve an equation. Okay, so if you realize, right, when you try to solve for an equation, actually most of the time we can only solve very simple equations. Okay, simple equations in the sense that like linear equation you can solve. Mx plus c equals to some number. That one you can solve for x. Okay, and polynomials, quadratic formulas allow us to solve for the equation involving some quadratic function, okay, because we have developed or derived the quadratic root formula, the minus b plus minus root b squared minus 4ac, that guy, okay. But cubic, you try to solve cubic equations involving x cubed, then you probably have heard that, or you probably have learned that you need to do some guessing. You need to guess, right, look at the last constant, and then guess what are the factors, of that constant, okay? But truth is, there is also some formula, but the formula is horrendous. Then if you have quintic polynomial, which is degree 4, okay? That guy, the formula is horrendous. You can Google for that. Degree 4 polynomial formula to solve for the root, right? Horrendous, okay? Now the thing is, right, if I give you a higher polynomial degree, degree 6, then actually there is no general solution really. Okay, and in fact, for most equations, there is no analytical solution. Meaning to say I cannot mess around with the terms, right, bring to the left, multiply or whatnot, right, in order to solve for x. Okay, for example, this x equals to cosine x is like deceptively simple to solve. But if I ask you to find the values of x that satisfy this equation, there is no so-called mathematical, analytical way to do it. Okay? One can do it by what? One can do it by plotting a graph. Okay? So if you want to solve, okay, so if you want to solve x equals to cosine x, right? What one can do is to go to a graph plotter, type in y equals to x, type in y equals to cosine x. So what do we mean by x equals to cosine x? The intersection. So there's only one solution. The solution is 0.739 something. Observe that. Okay, so x equals to cosine x means the intersection point of the two graphs there. So that's one way you can solve. Okay, but certainly we don't want to have manual intervention, because sometimes when we write program, right, and we are tasked to solve these equations, or in the process we are required to solve certain equations, we do not want to have manual intervention such that, right, we need to look at the graph and then we key in the value. We want the computer to do it automatically, okay? So which means we need what we call a numerical method to solve this, okay? So what is a numerical method? Numerical method, right, is just a method that is iterative in nature. Meaning to say, you just repeat the same calculation and you will get closer and closer to your answer, under some conditions, of course, okay? So let me introduce you a numerical method here, which is called the bisection method of root finding, okay? So let's go through an example to understand this easily. Now let's say I'm trying to solve x equals to cosine x. So one way to write it, right, is really bring the cosine x to the left-hand side, and then you get x minus cosine x equal to 0. So I name this equation, x minus cosine x equals to 0. I name this function f of x. So which means that I'm really trying to find the root of x minus cosine x. Okay, I want to find the root, right? Because that's what gives the function to be 0. So now, what is the beginning of the bisection method? Now in the first place, right, you got to make sure that there is a solution for this equation inside some interval first. Because if, let's say, there is no solution, for example, looking at the graph here, what is the interval? The interval is 0 to 1. So your solution here lies, right, in between 0 to 1. Now, if I give you the interval 1 to 3, for example, then you need not even try to apply the method in the first place, because you will not get the solution. Because the solution is not inside 1 to 3, obviously, from the graph. Okay? So therefore, this begs the question, right? How can we check that the solution is indeed in that interval first before we apply some numerical method? And the answer is by the intermediate value theorem. Okay? So you can see here, right? Because we want f of x to be 0, right? And because f of x, let's say, we verify that it is indeed a continuous function. So what's going to happen is that we have an interval, let's say a to b. So in this case, right, so I found 0 to 1. So let's say 0 to 1. And what I do is very simple. Because I know that this guy will be 0 in between 0 to 1. Okay? How I know that? Well, I can simply check that there's a change in polarity of the function value. Okay? For example, I test. So this one is really trial and error, right? So if you sub in 0, 0 minus cosine 0, 0 minus 1 is minus 1. So you'll notice that this is negative. Okay? Negative. So which means that f of 0, I don't know where this okay, so this is negative. In fact, it's negative 1. Then what happens is that, right, I just guess another value. Okay, so let's say I guess 1. Then I notice that 1 minus cosine 1, I get 0.46. And this is positive. So therefore, at 1, at x equals to 1, I get 0.46, which is maybe somewhere here. So which means I don't know how the graph passes through the x-axis. But I know for sure that because x minus cosine x is continuous, that means no matter how it passes through, right, it must be cutting through the x-axis. So this is my guess. Maybe this is my guess. The graph looks like that. Okay? So you can see that there is indeed a solution. There is indeed a solution which is right here. So this is the root that I seek. Is that right? Okay? So therefore, in a nutshell, when we want to solve an equation, what we do is that we manipulate the equation such that we get equivalent to 0. Next, we check the continuity of the function. If the function is continuous, then we guess the interval for which there is a change of polarity of the function. Now, when that is confirmed, then we will use the numerical method to find the root. Okay? So this part shows the using of the intermediate value theorem to check for the solution. Is that right? Okay? So, if you understand this, right, then this exercise here, explain why cosine x minus x will give the same root as f of x. So what is cosine x minus x? Cosine x minus x is just minus of f of x. So from your topic 1, right, when you take a function and you multiply by a negative 1, what's going to happen to the function? I repeat it again. Hey, your quiz later. When you take a function, you multiply by minus 1. What is the transformation you do to the function? Flip it. Basically, you just flip the function vertically. So you just flip the function. So this function, right, become like that. And you'll be able to get the same root. Because you only flip it, you never do anything to it. You never shift it or what. So therefore, when you flip vertically, you're just having this symmetry about the x-axis. So therefore, right, oops, this should be f of x. So the green one is the g of x. The pink one is the f of x. Is that right? Okay, so you can see it's the same root. Okay? So when your f equals to 0, then g will also be equals to 0. Is that right? Because when f equals to 0, g also equals to 0. Right? So that means the root x must be the same. Is that right? Okay, so let's look at the numerical method. So after we verified that, oh, you have a solution inside the interval already, so really, we can apply the method now. Okay, this method is called the bisection method. By the way, for root finding, there's not just one method, there are multiple methods. Okay, and bisection method is a very robust method, although it's a bit slow, right, as you'll see one later on. There are faster methods, but bisection method is very robust in the sense that, right, it typically will not result in computational issues such as division by 0, stack overflow, that kind of issues. So, now, how does it work? So you can see that, right, basically given the interval a to b, so bisection, so basically you just half that interval. So a to b, when you half it, you see a plus b multiplied by half. So where's the half? The half is exactly midpoint between a to b. So let's call that m1. Okay, so this is the bisection, the first bisection. So after you have the first bisection, I know what you do. You compute the function value at the bisection, okay, at the bisected value, let's say m1. Now let's say if your f of m1, right, is negative. So what you do is that you just shift a to m1. Shift a to m1. Okay, then you realize that actually your a to b is now half of that interval, half of the original interval. Okay, so what do you need to do? Then you just repeat the same story. So you just bisect again. You get m2. Then you compute f of m2. Now if f of m2, let's say if it's more than 0, f of the bisected midpoint, if it's more than 0, then you move the b towards m2. That means you just let b be equals to m2. So you notice what you're doing now, right, is that you're continuously cutting the interval by half while straddling the root in the center. Okay? You can see, original interval contains this root. After one bisection, half the interval, still containing the root. After the second bisection, another half of that interval, still containing the root. So basically, you're squeezing towards the root. You're squeezing the interval towards the root. Is that right? Can I? Okay, so I hope graphically this makes sense. So then when do we stop? Well, we just repeat until you found the root or the maximum number of iterations you have reached. Because you cannot do this forever, right? Because it's possible that you didn't check your IVT and then you realize that there's actually no root inside. Then you keep on just running forever. You never find the root because there's no solution in the first place. Okay, so you need to have a maximum number of iterations. By the way, are you doing programming now? Good. Okay, excellent. So you have a chance to practice the bisection method. Okay? Yeah. Okay, so I'm going to just show you some manual computations before I show you the program for ease of understanding. Okay, so let's continue to solve this. X minus cosine x equals to 0 in the interval 0, 1. So you see what practically we do is we just calculate the midpoint. 0 plus 1 over 2 get 0.5. F of 0.5, so sub into the formula, 0.5 minus cosine 0.5, then you get a negative number. So because this is negative number, right, so I move the left end point, point A, to the new midpoint, okay? So A will be 0.5 now. You can see I assign A to M1. Then subsequently, I just repeat the same thing. So it's A plus B, right? So 0.5 plus 1 now, divided by 2, 0.75. Calculate F. I realize that F is more than 0. So therefore, since it's above 0, I move B. So B is now moved to 0.75. So A is at 0.5, B is at 0.75. Now I repeat the same thing. Okay, calculate the function value, and I realize that F is now minus 0.186. So I calculate that, and I realize that it's more than 0. So therefore, is that correct? Oh, there's a mistake here. So because this is more than 0, or this is less than 0, error, okay? So because it's less than 0, I move my A. Is that right? Okay. So you can see that my interval A to B gets less and less. That means it gets smaller and smaller. Right? So after A is assigned, you notice that the interval is just 0.625 to 0.75. Okay? So it keeps on squeezing towards the root. Okay? Of course, I can do this for multiple number of times. So this is the manual calculation. And what we do is really to just implement this in the program. So this is what the program can look like. Okay, so I'm just going to use Python to demonstrate. You can use any program you prefer. Okay? So this will allow you to solve some of the tutorial questions testing on this thing. You see? So I just define the function, and the function is just returning x minus math.cosine x. So this is just cosine x. Okay, math is the module or library that involves cosine x. So you see the interval 0 to 1 inputted. Okay, then this part I will explain later on. Just ignore about this part first. I declare the maximum number of iterations as 1000. Okay, you can put in any number. So then this is what? This is the tolerance for f to be close enough to 0. Okay, so what is this? This means because you can keep on doing the iteration forever. So as long as f is close enough to 0, because we are trying to solve f equals to 0, as long as it's within this tolerance to 0, that means, let's say, for example, 4th dp here, you can choose any precision you prefer, right? 6 dp, 10 dp, doesn't matter. Okay, doesn't matter. This one is up to your preference. Of course, in the question I may state. So therefore, bisection method will start now. So this is just a counter, I equals to 1. So while the counter is less than the maximum number of iterations, I just do my bisection, compute the midpoint, compute function value at the midpoint. So I call the function, pass in the midpoint value. That's why I define the function here. Okay, I can define any function here. Right? So you can see many functions here, right? Right? Some of the functions are given in your tutorial 2. Okay? So after that, you can see that this part is basically to just reassign A or B. Reassign A or B. Okay, so you can see that if, let's say, your function value is very close to 0, such that it's within the tolerance, then you can just print root found. Root found. Then what's the solution? Solution is just the midpoint value. Simple as that. Okay, subsequently, break out of the loop. Break out of the loop. Hey, by the way, where's your programming at now? You all learn loops already. Just right. Okay, so else if. So if your function value less than 0, assign a to m, exactly what we did earlier. Right? If your function value more than 0, assign b to m. Okay? Can increase the counter, right? Because you need to check whether it's maximum iterations or not. Okay, then after that just print. Okay, this printing is just for monitoring. Okay? You print the midpoint, right, for monitoring, right? So therefore, in this case, if let's say you hit the maximum number of iterations already and you still have not found the root, then basically you just print a statement that the solution is not found. Okay? So if I run the code here, right, you can see the fella here. Can you see? Alright? So the midpoint, can you see? So the solution is 0.73913574. 739, right? So that is going to agree with our value here. 739, can you see? Is that right? Okay. So by right, of course, the bisection method, if you do it correctly, it must be in agreement with what is shown on the graph here. Any questions on the program? Okay, good. So, of course, I will share the Python code with you. You can convert into C++ or C or whatever, okay? But if you don't want, you can just directly use Python. It's up to you. Okay, so that you can solve the tutorial questions. That's good. Okay, so last exercise for today, and then I'll let you take a break before we do the quiz. Okay, take a chill break. Right. Okay, so let's apply. Let's apply. Right, so it's supposed to find the interval for which the solution to the equation below lies. Okay, so we just define a function f such that you get right-hand side equivalent to 0. So this says there's only a 2 on the right-hand side, right? So therefore, I'll just bring the 2 across for ease of calculation. So this one equal to 0. Okay? Can Yeah, then now, right, I need to trial the interval. So trial the interval where root lies. So basically, I'm trialing the interval AB. Okay, I don't know where is AB, but I can just trial lah. I don't know Cannot. So you see, just by virtue of looking at the equation, right, you should, probably the function is not too complicated, but from this equation, from this function here, you notice that, right, as your x goes big, it's going to be positive. As your x, because the dominant term is x squared, by now I think you know. Okay? So this dominant term is x squared, so as x is big, then this dominant term will make your f approach positive infinity. So that means to say, right, don't trial too big an x value in the first place. Okay? So therefore, maybe you can trial x equals to, let's say, for example, say 1 or 0. Okay, maybe I trial 0. 0 is the best. Okay? So f of 0. So what's f of 0? 0 squared plus ln 2 minus 2. Okay, then let's calculate ln 2. Ln 2. So ln 2 is 0.693. So obviously, 0.693 minus 2. Okay? Sorry? Oh, it's plus 1. Oh, my bad. How can I put 2? Apologies. So it should be ln 1. Ln 1, my bad. So which means that it's 0 minus 2. 0 minus 2. So it's minus 2. So obviously, minus 2 is less than 0. Okay? So therefore, I want to find a b value such that, right, my f becomes positive. Okay? Then certainly, right, I can choose any big enough x. Okay? But if you want your bisection method to converge to the root fast, right, then of course, don't make the interval too big. Of course, you put in 1,000, you're definitely going to see the root inside. Okay? So from here, I think if you try f of, let's say, 2, right, you'll get it already. So this is 2 squared plus ln 3 minus 2. Okay? So you can see this is 4, then ln 3 is positive also. So 4 minus 2, right, is definitely positive. So therefore, this number, I need not know it, but I know for sure that this is more than 0. Because 4 minus 2 is already 2, which is positive, and ln 3 is also positive. Okay? So which means that I found the interval whereby you have a change of polarity. So I just assign A to 0, and then I just assign B to 2. Okay? So therefore, I found the interval where there is indeed a solution. Okay? So then, of course, I must also make sure that this is continuous. So I can say that because x squared is continuous everywhere, and you can see that, right, in the interval from 0 onwards, this ln is defined. So therefore, that's continuous as well. Okay? So I can state, since f of x is continuous in 0 to, there is at least one solution by the IVT. Okay? According to the intermediate value theorem, right, there must be at least one solution in that 0, 2. Is that okay? Yeah. Okay, so once this is done, actually what we need to do is to just enter this formula into the program, as well as adjust the A and B interval values to make sure that you are straddling the roots. So it will be this one. The second one, can see? So return x squared, x star star 2, that represents x squared. Then ln x plus 1, then minus 2. Okay, then remember to update the interval, so which is from 0 to 2. Okay, then with that, right, we just run the code. So you can see, starting from 1, okay, the first because 0 to 2, so the first bisection point will be 1. Then after that, we found the root, and the root is approximately 1.117 something. Is that right? Okay, so this is using the bisection formula. Any questions? Any questions on the bisection method here? Can, as well as the intermediate value theorem. Okay, so the last part I want to go through with you, right, is actually a minor detail on the algorithm. Okay, so can you see the algorithm here? You notice that there's this part, right, whereby I need to sort A and B. You see this part? Okay, so I mentioned here that if you have f of A more than 0 and f of B less than 0, then you have to sort A and B. So this is exactly what happens, right, when you define, for example, the function g instead. Okay, if you define the function g, if let's say this is your g, right, that means this part is positive. F of A is more than 0. F of B is less than 0. I repeat that again. F of A is more than 0. F of B is less than 0. So therefore, if you look at your code, right, it conforms to this condition here. F of A is positive, F of B is negative. Okay? Then in that sense, right, you need to sort A and B. You need to sort A and B. The reason is because of the condition that you applied here. Okay? Because if you have defined that G function instead, then by right, if you don't want to sort A and B, you can. But this part you have to manage. Meaning to say, this is less than 0, right? Then you've got to move B instead of A. So therefore, instead of moving the A and B here, right, which will require more if-else statements, we might as well just keep the story simple, right, and then just sort your interval. Okay? So meaning to say, what is this doing? Graphically, right, is flipping this G horizontal. So we flip the G, because your A and B swap, correct or not? If your A and B swap, the G, right, you're swapping, you're flipping it. So the fellow become like that. So if the fellow become like that, it looks like F already. So therefore, you keep the same algorithm for the bisection. Okay? So this is just a minor detail on the program. Because if you don't do that, right, you realize that your program cannot work for some functions. Okay? So you have to consider multiple scenarios whereby it could break your program and then handle those exceptions. Okay? Yeah, so I think with that, that's it for this topic 2. Okay? So some cute comic for you to read. Okay, now 2 p.m. will start your quiz exactly. So 2 to 3, So now you have about 15 minutes. So what I need you to do is to get your laptop ready. Your laptop will only be showing the quiz page. No other pages to be shown. Okay? No other websites. No communication. No Discord. No DeepSeek, no ChatGPT. Okay? Only the quiz web page. So where's the quiz web page? I will supply you through Excite. Go to your Excite. Okay, you can access the link, but I'll open the quiz exactly at